welcome back. You're going to talk about logarithmic functions today and Wednesday. Those are going to be the last two lessons that will appear on test 3. Okay, test 3 is going to be Monday of next week. So we got 2 lessons this week. Friday we'll have a review class, Monday test 3. And on Wednesday I'm going to give you a take-home quiz. Do Friday and then test 3 on Monday. Okay, so let's look at the switch and solve strategy for finding an inverse, right? So it's been a little while since we talked about how to find inverse functions. The switch and solve said first replace f of x with a y, then make all the x's y's and the y's x's, and then the next step is solve for y, right? How do you solve for y in that equation? The y root, is that what you said? So how would I type that in my calculator? Like, what does the y root mean? I want a number that when you multiply it times itself, y times, you get 2. Right? Yeah. But y is a variable, right? Yeah, it's a little weird. Turn it into a fraction how? Okay. You don't know because we don't have a tool to do this yet. There is no algebraic tool that we know yet to solve that equation. Here, we're stuck. Okay. So here's a simpler version, right? Instead of having x's and y's, I've just got some numbers here. 25 to what power gives me 5? Yeah, say it louder. 1/2. 25 to the 1/2 power is 5. Because remember, when you have a fractional exponent, the top of the fraction is a power and the bottom of the fraction is the root. So this actually says the square root of 25. There's a 2 in the root and a 1 on the power. Very good. All right, so a little summary about inverse functions. We're going to be talking about inverse functions today of exponentials. Only one-to-one functions have inverses that are also functions. To test if a graph of a function is one-to-one, you can use the horizontal line test. If a function is one-to-one, that means its inverse function can be found by interchanging x and y in the function's equation and solving for y. The domain of a function f is the range of f inverse, and the range of f is the domain of f inverse, right? A function and its inverse, the domain and range just swap. The graph of f inverse is the reflection of the graph of f about the line y equals x. So if you want to graph f inverse, just pick some points on f and swap their coordinates. Make the x's y and the y x, and you'll have points on f inverse. Because inverse functions undo each other, when you compose two inverse functions, you get x back, right? You get the round trip. Put an x into the function f, and then put the result into the f inverse machine, and it just gives you the x back. Okay, so last time we talked about inverse functions, and we said an exponential function, b to the x, any number to the x, is 1-to-1. Okay. So we know this because no matter what value we choose for b, we always pass the horizontal line test. So I picked 2 examples, the 2 basic flavors, exponential growth and exponential decay. So here I had b as 2, and here I picked b to be 1/2. Both of these graphs pass the horizontal line test, yes? Okay. So we know that these 2 functions have inverse functions. Okay, they're 1-to-1, so they have an inverse. So the goal of today is try to figure out what is the inverse function of an exponential. We know it exists because it passes the horizontal line test. What is it? So let's start by drawing it. Okay, An exponential function is 1 to 1. We know it has an inverse function. Here's 2 to the x. I want to sketch its inverse function. Okay, so I'm going to pick some points on 2 to the x, swap their coordinates so that I can graph the inverse. So let's see, that's 0, 1, 1, 2, 2, 4, 3, 8, 4, 16. That should be enough to get me started, right? So instead of 0, 1, I should plot 1, 0. Instead of 1, 2, I should plot 2, 1. Instead of, oops, no, that's right, okay. Instead of 2, 4, I should plot 4, 2. Instead of 3, 8, I'm going to plot 8, 3. And instead of 4, 16, I'll plot 16, 4. So if I connect those with a nice smooth curve, can you see that it's what I've drawn in orange is a reflection of what was there already over the line y equals x? Put in the line y equals x there. So that's like my mirror line, y equals x. So it's a reflection. Now, how do I draw the reflection of this part that has an asymptote that's the x-axis? Down with an asymptote is the y-axis. Yeah, so I just draw it like this. So this is f inverse of x, right? The question is, what's its formula? Okay, I've got a picture of it. It's the inverse of 2 to the x, and I would like to know its formula. To find a formula for the function we sketched, we do the f of x equals 2 to the x and interchange x and y and solve for y. So this is what we tried to do in our preview, x equals 2 to the y, and we get stuck trying to get the y by itself. Okay. So we don't have a mathematical way to solve this equation yet. Okay. We need to undo raising 2 to something, right? Raising something to the 2 is easy to undo, right? You square root, but how do you undo raising 2 to the something? So we invented this function that undoes raising 2 to the something, and it's called log base 2 of y. All right, so go back up here to x equals 2 to the y. And I'm going to take log base 2 of both sides. Log base 2 of the left, log base 2 of the right. So on the left, I get log base 2 of x. And log base 2 of 2 to the y undo each other, right? So I just made up a name for it, called it the log base 2. It's the thing that undoes 2 to the y. So if you take log base 2 of 2 to the y, you get the y back. Okay? You don't get the 2. The 2 goes away. I invented a function, not me personally, right? Mathematicians invented this function so that it would get the y by itself when you were raising 2 to a variable. You could take log base 2 of it and it will get the y by itself. All right, so I know this is weird, right? So this is the formula for my inverse function that we just drew, log base 2 of x. So I could write it up here. This is log, oops, log base 2 of x. All right, we're going to get into some more details about what this log thing actually means, okay? So the definition of a log function. This is the important thing. It says that if you write y equals log base b of x, that is equivalent to writing b to the y equals x. So those two equations are different ways of expressing the exact same information, right? The exact same equations. They're equivalent equations. Just like 10 over x equals 5 is equivalent to writing 10 equals 5x. Those are equivalent equations. They tell you exactly the same information. Okay. If y equals x and y equals 5x over 5, right? Those are equivalent equations. They have the exact same solution sets. Okay. So just like these things are equivalent equations, log base b of x equals y and b to the y equals x are equivalent ways of writing the same information. So let's look at some examples, right? If I give you a log, an equation that has a log in it, you should be able to translate it to an exponential equation using this equivalency. So if I give you an equation with a log in it, you can translate it to an exponential. Okay. So let's look at where the pieces translate. Okay, so I have y equals log base b of x equivalent to b to the y equals x. So in the exponential, right, y is my exponent, right? Where does y appear in the log equation? All by itself on one side of the equation. Okay. And then the base is kind of handy the way we call this the base and we call this the base, right? In both of those equations, b is called the base. So in a log, it's the little subscript, the base, and in the exponential, it's the base of the exponential expression. And then x is the only other thing left. So if you remember which one's the base and which one's the exponent, x is just the other thing, right? All right, so let's do an example. I have log base 3 of 9 equals 2. Which number in that whole expression is the base? 3. Yep. Which number is the exponent? 2. The number all by itself on one side of the equal sign is the 2. And that should equal the only remaining number, 9. 3 squared equals 9. It's a true statement, right? Okay. So these are just two equivalent ways of stating the same information, that 3 squared equals 9. Log base 3 of 9 is 2. So one like mnemonic that people use, I guess not a mnemonic at all, logs are exponents, right? So here's a log. It is equal sign an exponent. So the log of some stuff equals something. That something is an exponent. A log is always an exponent. Okay. Logs are exponents. Yeah. All right, let's do one more example. Which number, -1, 8, or 1/8, is the base in this equation? 8 is the base. Which number is the exponent? -1, and that should equal the only remaining number, 1/8. Is that true? Yeah. 8 to the -1 is 1 over 8. Okay. These are just equivalent ways of writing the same information. All right, so let's see if we can go the other way. So I have some exponential equations, and I want to write them as log equations. So I'm looking for log of something, log base something of something equals something. There's 3 numbers I have to put in here. In 2 cubed equals 8, what number is the base? 2 is the base. So 2 goes in the little subscript. Which number is the exponent? 3. And the exponent is always by itself on the other side of the log equation. So I put the 3 over here. The only other number is 8. Log base 2 of 8 is 3. Right? So the log is the exponent. Log equals exponent. All right, one more. 6 to the -2 equals 1 over 36. So log base 6. Yep, my base is 6. And then what do I put on the right-hand side of the equal sign? -2, that's the exponent, yep. And then the only other thing is 1 over 36. You can put parentheses there. It means the same thing with or without. Sometimes it just looks a little clearer if you put them. So this kind of like, okay, so there's another way to write exponential information. Okay. So I'm going to evaluate some logarithms now. Right. So I'm going to have to translate this to an exponential question in my head because I'm not used to answering log questions. Right. So log base 10 of 100, they're asking me, what does that equal? Right. So what goes on the other side of a logarithm? Y, which is which part of the exponential equation? The exponent, yeah. So 10 is my base, right? 10 is my base. I don't know the exponent, equals 100. Okay. So what exponent do I put on 10 to make a 100? 2. So that is the answer. Log base 10 of 100 is 2. Yep, so the answer is 2. Yep. Okay. Log base 5 of 1 over 125. So I'm asking, what power do you raise 5 to? What is the exponent that you could put on the base of that base of 5 to make 1 over 125? So I'm asking 5 to what power equals 1 over 125? -3. Awesome. So the answer there is -3. The exponent that you put on the base of 5 to make 1 over 125 is -3. Okay, log base 36 of 6. Right? So my base is 36, right? Base is 36. The exponent I don't know. What can I raise 36 to make a 6? The 1/2. 1/2. Because 1/2, raising to the 1/2 is the same thing as square rooting. So 1/2. All right, so logarithms are the inverses of exponential functions. So think about when you first learned multiplication in what, like 3rd grade, right? You first learned how to multiply. You spend forever talking about how to do multiplication, and you work on it, and you work on it, and you work on it, and you do 2-digit numbers, and like you get better and better at it. And then the next year, they're like, let's do division, right? And it feels like this crazy weird thing, but it's really the same. It's just the undoing of multiplication, right? So this feels like this crazy weird thing, but it's just the undoing of something we already know, exponentials. Okay. So it takes a little time to get used to it, but you will, and you can start now working on your activities.